Good morning, all of you. I'm audible. Hello.
Yes, sir.
My screen is visible, ma?
Yes, sir.
Okay. See, we'll start today actual subject. So far, we discussed the introduction of all the controllers and overall subject. So now you may be familiar with all the topics briefly, so that it is easy for you to understand the concept and all, and also for lab purpose. Now we start directly with silicon controlled rectifier, that is SCR, that is a second unit. All the devices, first two units are the devices, and first unit is the diode, BJT, MOSFET, IGBT. That basic things are already known to you. That's why it is quite important throughout the subject. And also for lab purpose also we must start with SCRs, because all the experiments related to SCR only. Whatever experiments we are going to do in the simulation as well as the hardware, we required as a SCR. So that's why I start with SCR, then only I will go to the basic devices, CJT, MOSFET, IGBT and all. That is not required for the lab purpose at moment of first cycle. In the second cycle, if it is hardware only, we'll use that characteristics of BJT, MOSFET and all. Otherwise, it is not required. So that's why I start with SCR first. Once if it complete, then we'll move on to that characteristics. Then only we'll go to the controllers. Now, you can see this silicon control rectifiers. In this unit, the presentation agenda, introduction, then static characteristics of SCR, then turn-on methods of SCR, because if device is there to turn on, we need to use some of the methods. Directly it won't be happen. As you know that SCR, normally if anode is positive with respect to cathode, device will not turn on directly. We have to use some methods, preferably in that which is the best one we will use in normal case. But we have some more methods to turn on the SCR. Generally I explain in the all the introduction classes, there is a one gate. If you give gate pulse, then only device is going to be turn on. That is one of the method, but that is simple method and also efficient method. That's why we are using in general all the cases. Firing pulse we are given to the that one, but we have other methods also. We'll discuss that. So that's the, because this is all unit, no, we have to go in detail. So whatever we discussed so far, that is all only the introduction. But now we move on to unit wise, so it go to in detail. That's why you can see that turn on methods of SCR. We have nearly 5 methods. So individually we will discuss that. And which one is a preferable one, we will select that. Next one is a two transistor analogy. I think this also I quoted in the introduction classes. Directly SCR is there to operate, or else you have a transistors, two transistors, that is NPN transistor and PNP transistor. Make use of that two transistors to operate as a SCR. Either you can use directly SCR device, same performance, or else use two transistors to operate as a SCR. That is one of the topic. And another one, dynamic characteristics of SCR. What is dynamic characteristics of SCR? And the first one, static characteristics. There we'll see the VI characteristics. Now dynamic characteristics means here the device is in the off state initially, and you are applying some turn on methods, and device is going to on. while it is off state to on state, that dynamic things inside what will happen during that process, that we call it as a dynamic characteristics of during on process. Similarly, a device is already a on state. Now we are going to turn off the device. Initially is in the on state. After that we are going to turn off the device. For that also you need to do some process, or it may happen inside. That thing we need to find out what are the things going to happen during on to off. All this scenario we call it as a dynamic characteristics or switching characteristics of SCR. Both are same. If I call it as a dynamic characteristics, are also called as a switching characteristics of SCR. That also very important thing. We need to analyze from off state to on state, as well as on state to off state. This process, in between there is a some sub intervals are there. That thing we need to find out or analyze through graphically. That is, we call it as a dynamic characteristics of SCR. Another one is a protection of SCRs. So protection is very important of any equipment or a component or a device or anything. In this also, for SCR also, we have some protection. That protection, like a snubber circuit protection and over voltage protection or a current protection. So all these things we will discuss in this topic, that is a protection of SCRs. And another one, series and parallel operation of SCRs. So here you can see that I already explained why series operation and why parallel operation. So here, to increase voltage demand or to increase the voltage levels, we can use as a series operation, or to meet the voltage demand. Another one is a parallel operation, to meet the current demand in the load side. For that reason, we need to connect many number of SCRs or in series or in parallel. That depends on your demand. Whether demand is a voltage demand, connect more number of SCRs or in series. How many number, that will decide by your load demand. And similarly, if demand is a current demand, then you have to connect number of SCRs are in parallel. But each SCR rating is known to us while you are buying the component. You know your demand or you know your application. Based on that, you have to select your component, and that component, if that one component is not meet the required load demand, you have to connect many number of SCRs or in series or in parallel. So that is the one of the topic. And other one is a triggering circuit. So here, why the triggering circuit is required, this also I explained in the previous classes. To fire the device, like methods we explained in the upper topics. No, there is a third one is a turn on methods of SCR. There some on process are there. That is all the some of the thing, but in general we don't use some of the methods. We will use only the which one is a efficient method. In that we have subtopics. There is a triggering, or also called as a firing circuits. Both are same, don't confuse. Firing circuits or a triggering circuits. How the device is going to be on according to your given method. So that method may be different methods, but again there is, we have to discuss what is the drawback in that sequence of the methods. Finally, which one is a preferable, that method will be used to fire or to vary the alpha, nothing more. See, triggering or firing circuit is nothing but a, I said in the once at what instant device is going to be fired, that particular instant we need to use that one to fire the device. So that is the reason I want some cases I need alpha is 30 degrees, or I want more voltages. then you reduce the alpha. I need less voltages, then increase the alpha. That things will happen through this circuit. That the reason we need to discuss here as a SCR characteristics, SCR triggering circuits. And this one is a commutation methods of SCR. Now here all the things are related to SCR. Now we can notice that SCR can use any of the controller, whether a phase control rectifier or choppers or inverters or anything. So based on your input supply to the SCR, we need to find which method you have to prefer. By default, the phase control rectifiers, AC voltage controllers and step down choppers are natural commutation. That we don't discuss here because anyhow that will happen automatically. Only our discussion is here commutation methods, forced commutation techniques. Natural means any one of the circuit you can use. AC supply is given and one thyristor and one load, what we discussed in the class, lab the class yesterday, small circuit, that itself has a natural commutation, any one. But now here there is a forced commutation techniques. So in that forced commutation technique, class A to class E, all the are type A to type E, all the techniques are going to explain in this. So that's why each and every topic is related to the circuit and waveform only. Only your understanding is the operation you must remember. Otherwise it is difficult to remember directly as a graphs or a waveforms. That is a difficult task. That's why you try to understand circuit and waveform side by side. If you know the procedure and each point of time, then by your own you can able to plot or you can able to draw the waveforms. So that is only the scenario. So these are about the presentation agenda of this unit. We'll start one by one and we'll try to complete as soon as possible. And once if it completes, then I will conduct the exam, all these things. I will give the material and later I will add some of the soft copies of the textbooks, or you can go to Google Books, you can find that. But you just try to read the textbooks also, apart from the material which I am going to share to you. That will aware your topic, total subject. So now we'll see the introduction. As you are aware that this thyristor or SCR are same, I told this is a general term and it is a family of a power semiconductor devices. So there is a power semiconductor devices, many devices are there, SCR, BJT, MOSFET, IGBT, GTOs, triac. So like that, MCTs. So many of the devices are there. This is one of that family, and not only the SCR, there is a laser also will be there. This also one of the efficient device. This will be used normally in the accurate turn on laser beam you are passed to fire the device and all. For that we'll use as a light activated SCR, that is a laser, and GTO, that is a gate turn off device, and triac, triode AC, all these are the family of that. So these devices are used extensively in a power electronic circuits only. Normally all the controllers, whatever power electronics controllers are there, this type of devices will be used. Then there is a control on the conduction as well as the conducting and non-conducting states. While it is turn off, we are using as a forced commutation or a natural commutation. To turn on also, we required on methods, that is a conducting methods. And the conduction of thyristor is possible by providing current to gate terminal. This is the one efficient method, but this sentence is not throughout valid. There is a many methods are there, but why I mention is here all that methods are not efficient. Whatever available methods are there, that is not used in general case, are not preferable. That is the reason I made one simple sentence here. So not only the current to gate terminal, there is a other possibility also there. Like can see that this is a thyristor. Anyhow, that will come once again and on methods process and all. This is the thing. Let's see, this is a thyristor. Symbol for the thyristor. Now, what they are mentioning is statement in the above statement. If you pass current to gate, if there is a gate current IGI represent, there this will be limitation also there, minimum limit and maximum limits like this. So if you have that limits, then what we can do, there is a minimum gate current. If you pass, SCR is going to on. On means it is switch will be closed, current will pass like this. That is only the SCR is turn on. Either you can pass the minimum gate current, it will trigger, or you can pass some voltage across gate and cathode. If we close this way, in turn it is passing current, then also device is going to be trigger. There is one method. Or otherwise also there is anode to cathode. If you give some voltage like this, if you go on increasing this voltage, at some point of time device is going to be triggered like this. Many things are there, I will explain in that also. Yet moment this statement, conduction of thyristor is possible by providing as a gate current to terminal and gate and cathode, or directly gate current if we give, it will conduct, or gate and cathode voltage across gate and cathode. If sufficient voltage applied across gate and cathode, then also it will turn on. Or anode to cathode voltage, if we increase the up to the breakover voltage, it can trigger. But this method is a drawback method, that's why generally we don't consider this. Only this type of method is used to turn on the device. So that is the sentence. Not only the gate current, you can write if you want, voltage applied across gate and cathode, sufficient voltage or triggering voltage applied across gate and cathode, this is going to be fire. Another one, turn off of thyristor is also possible when the current flows through the device is 0 or below the holding current. This statement many times I mentioned, either 0 or holding current is no matter, anything can write. Strictly speaking, it is a below holding current. It is after all as a milliamperes of current. That's why generally in all conventional terminology will use 0 only in general case. Means to turn off the device, current passed through the device is below the holding or 0. Current is 0, then automatically it is going to be turn off. And most used in power electronic circuit, that is already mentioned. Now we'll see the static characteristics of a SCR. Now SCR is a unidirectional device. What is the meaning of unidirectional device? What is meaning of unidirectional device? Suppose if we have SCR and also another one of the device is a bidirectional device like a triac. You can see this track symbol will be like this. This is a triac. So now we can see in this case it will allow to conduct like terminals. If you want to convention, this is MT2, this one is a MT1 and only one gate, let it be. And this is an anode and this one is a cathode and this is a gate. So in this case, triac, it will start conducting from MT2 to MT1. It will allow, and otherwise it is also allow the conduction from MT1 to MT2, depends on your gate. Either gate can give positive or you can give the negative. In the both cases, this is going to conduct MT2 to MT1 or MT1 to MT2 is possible. This we call it as a bidirectional conduction. But whereas in this thyristor case, it never allow otherwise. So it will allow only anode to cathode. It will not allow to conduct from cathode to anode. During that instant, the device is a reverse bias. That's why the switch will be open. So only conduction is possible from anode to cathode. So that is the reason you can say that SCR is a unidirectional device. That's why in the AC voltage controller and all, because of this unidirectional device, to positive off cycle only it will conduct, but negative off cycle, if I connect to AC supply here, see that negative off cycle it won't conduct, no, it reverse bias. That is the reason what we'll do in AC voltage controller, you can see here two things we need to connect. One is a SCR1 for positive off cycle, for SCR2 for the negative off cycle. So these are the two things is possible in this. Now you can see for positive off cycle it will forward bias, for negative off cycle it is forward, but it means it is conducting anode to cathode only, but you will get the negative current. The reason is our reference current is like this. When the T1 is conducting, it represented positive. When T2 is conducting, represented as a negative. That means that it is not conducting from cathode to anode, but it is conducting anode to cathode only. With refer to the reference, I will represent as a negative current. So that means that it is a unidirectional device only. So that is why if instead of using two thyristors are in anti-parallel, you replace that with this one, then that is sufficient. So, but MOSFET is a low rating device. It will work replacing these two anti-parallel thyristors by triac unit bidirectional one, but this rating is less. That's why only low rating applications you can use as a triac, like a light control or fire control or very small rating of motors, AC motors and all, we can use it. Otherwise, you must and should use as a two anti-parallel thyristors. So that's why I mention as a unidirectional device. Now, thyristor, the structure, if I consider, it is a four layer. There is a PN. These are the four layers. Three terminals. What are the three terminals in a SCR? Anode, cathode and gate, and three junctions J1, J2, J3, because in the four layers are formed, no, each layer to layer there is a one junction or depletion layer is there. So that we call it as a junction. J1, J2, J3 are the three junctions, is a semiconductor device. So defined thyristor means it is a four layer, three terminal, three junction semiconductor device. So that is a simple sentence. And this may have ratings, very few volts to the higher kilovolt level, as well as the few amperes to the several amperes. So the current rating may available from small voltage to the higher voltage, and similarly voltages are that much, currents also few currents to the high currents are available. There is a basically three modes of operation. Normally thyristor has three modes of operation will be there. We'll see one by one. So first you can see forward blocking region, because while you are explaining characteristics, there is a three modes of operation you can explain, that's all. So that will give the complete characteristics of a SCR. First mode is forward blocking region or mode of operation or a region of operation, anything you can call it as forward blocking region, one thing. Second one is a forward conduction region, and third one reverse blocking region. So these are the three modes of operation. So forward blocking, what is meaning of forward blocking? Device is under forward bias but it is in the blocking state, means off state, that I call it as a forward condition of forward blocking region. Second one is a forward conduction region. So the device is in the forward bias, now it is going to conduct. Blocking means forward bias and off state. Second one, forward bias, now conducting state, means before gate signal and after gate signal, like that. And third one, reverse blocking region. So under reverse bias condition, what is the characteristics? So these are the three modes of operation or three regions of operation. Now this one is the structure of a SCR. So what is the structure? As I mentioned, SCR means 4 layer, 3 terminal, 3 junction semiconductor device or a switch. So now we can see what are the 4 layers. There is a layers are P, then N and P, N. So these are the 4 layers. P layer, N layer, again P layer and N layer. 4 layers. 3 terminals. These are the 3 terminals, means sectional terminals, and 3 junctions. What are the junctions? This one is a J1 junction, and then J2 junction, then J3 junction. So these are the 3 junctions are available: J1, J2, J3. 3 junctions and 3 terminal semiconductor device. And in general representation, symbol will be like this. This one is a structure and this one will be the symbol: anode, cathode and gate. Now we will see one by one. First one is a forward blocking mode of operation. So in a forward blocking mode of operation, the connections are like this. What is this connection? 4 layers, no? PN will be there. Here gate will be open, not yet connected. That also one of the mode is there. I will explain after this. At moment, forward blocking mode means anode is connected to positive, cathode is connected to negative. So in that, how many junctions? 3 junctions. So all the cases 3 junctions. If all the junctions are breaks down, then I call it as a conduction. Otherwise, if any one of the junction also reverse bias, means not open, then that mode I call it as a blocking mode. Means the device is in the off state only. To turn on the device, you must and should open the all the junctions or breaks down. So in this case, if I give connection like this, plus is connected to anode and minus is connected to cathode, what are the junctions are forward bias. Now plus is connected to P, so let it be J1 is forward bias, and minus is connected to N, then J3 is forward bias. During this instant, we can represent J1 and J3 are forward bias condition. But now, what is status of the device? Whether I can call it this device is on state? No, because to turn on the device, this junction also must be breaks down. Otherwise, what will happen? It will come like this. It will stop here. No, there is a what we can call it as depletion layer is present in the junction J2. By means of whatever you want to do, you can do, and you break this junction, then only I can say that all the junctions are breaks down, current will pass through that. Yet moment we can see notice that one of the junctions are not breaks down. That mode of operation I call it as a forward blocking mode. So forward blocking mode means anode is positive with respect to cathode and junction J1, J3 are forward bias, J2 is reverse bias, and because of the depletion layer present at junction J2, no current pass through the anode to cathode. So except very small leakage current. That current is not sufficient to break the junction J2 and hence this state I call it as a forward blocking mode of operation. Now we'll see the reverse blocking mode. What is the reverse blocking mode? This mode means that you can make cathode is positive. So you made cathode is positive with respect to anode. Then what will happen? You can notice that if this is connected to the cathode and negative is connected to the anode means P layer, then what will happen? Junction J2 only the forward bias and then J3 and J1 are reverse bias. So you can see that J2 only the forward bias and J1, J3 are the forward bias. That is the reason this also has a blocking state or off state. Why I call it as a blocking state? Only one junction is open here, but rest of the junctions are reverse bias. This has to breaks down. Otherwise, no current will pass through the device. That I call it as a reverse blocking mode of operation. Only simple statement. Cathode is positive with respect to anode and hence J2 will be forward bias, J1 and J3 will be the reverse bias. This mode I call it as a reverse blocking mode of operation. And now this explanation through some small circuit. So this circuit, by make use of this circuit, you can able to operate your SCR or you can able to draw the characteristics of a SCR. For that, our intention is what here? To break the junction. That's all. Or to turn on the SCR at moment. That's the SCR. And as you are aware that the SCR is a switch. If switch is closed by means of gate or whatever method you want to adapt, if the device is on, means that whatever I represented across the device is VA is there, no? VA means voltage across the SCR or anode voltage, or VAK anode to cathode voltage, or VT, whatever may be the notation you follow, that is fine. Now once device is on means that shows that voltage across the anode or across the device will represent the 0 or 1 to 2 volts alone. So that means that by seeing the voltmeter we can easily identify whether the device is on or off. If it is on means voltage will be 0 except very small voltage, and if it is on means automatically 0, off means voltage across the device same as the source voltage. So with that logic also you can able to find whether on or off. And two processes are there. One is you open the switch here, S switch, and you can operate to turn on the device. That is one way. Other way is you can give some voltage across anode to cathode and close the switch S and you vary the resistor to turn on the SCR. So that way also possible, and otherwise you are changing the voltage across anode and cathode also possible. So we'll see both options and we'll decide which one is a preferable one. And now we can start with first mode of operation, that is a forward blocking mode of operation with characteristics V and I. So in that you can see what is happening is here or here any circuit is saying. Now we can carefully understand. I open the switch, yes, means forget about this portion. Let assume that this thing is not there. Open the switch and means it will not be there. No, by default open the switch, no connection to gate. That's why switch S is open, so gate is not connected. Then what is connected? Only anode is connected to positive, and then cathode is connected to negative. So anode is connected to positive, cathode is connected to negative. Then there is a voltage across anode and cathode that will read the voltmeter. You can see that voltage, one terminal is connected to anode, other terminal is connected to cathode. I used these small diagrams for your explanation purpose only. In exam, that is your choice whether you want to use or may not be. You can use this circuit, and if you draw complete characteristics, that is also sufficient. Now, what is the observation in the characteristics? You can see that VA means voltage across the thyristor, and the y-axis I will represent as a current. So now we can see that if I increase the voltage across anode and cathode, what will happen? You can see, how will you increase that? By increasing what? Potential divider, or by varying the potential divider or a rheostat, you are trying to increase anode voltage and cathode voltage. If I increase anode to cathode voltage gradually, you can see that this gap, normally what I said, if anode to cathode voltage applied some voltage, current will be zero because device is not turned on except small leakage current. So that's why I shown some gap here. Instead of directly x-axis, I made it some graph. So that graph will give what? As a leakage current. So once, if I increase anode to cathode voltage gradually, leakage current also will increase. Why leakage current will happen? Thus, even though J1 and J3 are forward bias, J2 is reverse bias, because of the junction resistance, once if a voltage is applied across that, because of the junction resistance, small leakage current will happen inside. That is very small, you can neglect also, but our characteristics to show that I am representing something gap. This gap, you can see this gap, I call it as a leakage current. And one thing you notice, if I increasing the voltage, x-axis is voltage, no? If I am increasing the voltage, gap also will little bit increasing. What is meaning? If anode to cathode voltage increases gradually, leakage current also gradually increases. So like that, you are getting as a increasing the voltage or a gap here, leakage current will be gradually increases. Now how long you can increase like that? If you apply that anode to cathode voltage further and further, then junction J2 may not be withstand, automatically junction J2 is going to breaks down if you provide sufficient voltage or a breakdown voltage across anode and cathode. So that's the point we represented here. VBO is nothing but a breakover voltage, forward breakover voltage. That means that much voltage is required from anode to cathode to break the junction J2, because already J1 and J3 are all forward bias. only J2 is a reverse bias. Our intention is to break the junction J2 to conduct. So first mode of operation is only forward blocking mode of operation. So you can write only up to VBO before breaking the junction. So what we will do is anode is positive with respect to cathode, J1, J3 are the forward bias, J2 is reverse bias, and we are applying some voltage, gradually increasing the voltage across anode to cathode. The leakage current gradually rises, but this leakage current is insufficient to break the junction J2. That state I call it as a forward blocking mode of operation. That's all the first subheading. This is what I can see that we are increasing some resistance we need to provide. Suppose if it breaks down, very high current will pass through that. To limit that current, we are using as a some resistance in series with the diode thyristor. So that way, that is only the for internal protection purpose at moment. Now what we can do, next mode of operation, we can see what is happening. Next mode is what? Simply I am further increasing this up to, before breakover I explained for mode 1 operation. In mode 2 operation or second region, that I call it as a forward conduction region. What is the forward conduction region? Now increase this voltage through potential divider by increasing the anode to cathode voltage by varying this rheostat. Then gradually this is going to be, means this is a depletion layer is going to be breaks down. The reason is there is a width of the depletion layer is inversely proportional to the applied voltage across that layer. That is very direct relation. Width of the depletion layer, because there is a some flow is stopped at this moment, there is a some width depletion layer will be present. You can see in this area, this is a width of the depletion layer. So what we'll do, we are applying voltage across this point, some voltage. So now this width will be inversely proportional to the applied voltage. Now if we are increasing voltage gradually by varying something, and what will happen, the width will be gradually dropping down because we are increasing the voltage. So voltage is increased across anode and cathode, width of the depletion layer will be decreases. Now the width will be like this. If further increases, now the width is very thin line, and after that if I go on increasing the voltage, that uh, depletion layer is going to be breaks down. Once the depletion layer is breaks down, means junction J2 is breaks down, already J1 and J3 are already breaks down because it is a forward bias, and reverse bias junction J2 is breaks down. Once if you apply this anode to cathode voltage, then what is meaning? The device is going to be on. Sharply high current pass through the device. To limit that, we are using as a one resistance in series with that to protect high currents. Now we can see what is the characteristics. In earlier, this red line represent voltage, and gap is the leakage current. This voltage will be gradually increasing. Finally, once if you apply the voltage across anode cathode up to the VBO, immediately thyristor starts conducting. Once thyristor is conducting, that voltage, what will happen? Voltage will sharply drop down to 1 volts or 2 volts. 1 to 2 volts only voltage will be available. But what happened to current? Current will be increases rapidly. That's why you can see the current line. This y-axis is the current, x-axis is a voltage. So voltage is gradually increasing earlier up to VBO. Suddenly it is dropped down to what voltage? Only this much voltage. So this voltage is very small at this point. So voltage is dropped down to 0 level or 1 to 2 volts. But current, what will happen? Current will be gradually, very sharply rising because no other obstacles, no, it is all junctions are breaks down. Current will be sharply rises. That mode, I call it as a forward conduction mode of operation. There is a two modes is over. One is a forward blocking mode. Up to before breakover, you just gradually increases the voltage, then only small leakage current that is insufficient to break the junction J2, and we call it as a forward blocking mode. And now after, you can start writing, you increase the anode to cathode voltage further and further because of the voltage is inversely proportional to the width of the depletion layer. That's why what will happen, the junction J2 is going to be breaks down if you apply sufficient voltage across anode and cathode. That sufficient word is nothing but a breakover voltage. If the voltage across anode to cathode is equal to the breakover voltage, then the junction J2 is going to be breaks down. Current will be sharply rises. Voltage is dropped to the 1 to 2 volts. So that is the second mode of operation. And third one, you can see what is the third mode I explained. Reverse break blocking mode or breakdown. Later if you apply same method, breakdown also will be happen, but it is unwanted. We don't require to operate in that mode of operation. So that is a third quadrant operation. Will not be operate. Now for reverse blocking mode of operation means that cathode is positive with respect to anode. That is what supply is given. So cathode is positive with respect to anode. Then J2 is a forward bias. J1, J3 will be reverse bias. Now also will not allow any current pass through the junctions. So except small leakage current will allow at junction J1, at junction J3, but total current will not allow because the J1 and J3 are the reverse bias, J2 will be forward bias. That you can see the characteristics. Now we are increasing the reversely. What we are doing is we are applying the voltage cathode to anode gradually. Then this gap, same as in the forward condition, that this gap I call it as a, what you call it as, reverse leakage current. So by increasing the voltage, this gap will be gradually increases. That is a reverse leakage current will be gradually increases. And once it is increases, that mode up to this mode I call it as a reverse blocking mode of operation. And still further increases this voltage, and some certain point of time there is a voltage across cathode to anode is VBR, then the junction J1 and J3 is going to be breaks down. That mode I call it as a reverse conduction mode of operation. This voltage VBR I call it as a reverse breakdown voltage. VBO is a forward breakover voltage. And now what will happen, it will get directly sharp. It will not be linear, it will be very sharply it is going to conduct. This will not happen in a normal operation. So now the question will arise, which voltage is a higher voltage, whether VBO is high or VBR is high, which voltage is a higher voltage. So for this there is a small logic is there. Voltage is inversely proportional to the width of the depletion layer. So if you are increasing more voltage, width of the depletion layer will be decreases. Finally, it is going to be breaks down. That is the logic. So in that, to identify VBO is more or VBR is more, what is the logic is here? When device is in the forward bias condition, the width of the depletion layer means forward bias condition means J2 is the width, no? Width of the depletion layer at junction J2 is greater than sum of the width of the junction J1 and J3 during reverse bias condition. Now tell me which one we need more voltage. So this width of the depletion layer is more during forward bias condition, and this width is less when during reverse. Sum of this width J1 plus J3, this sum of the width during reverse bias condition is less comparatively J2. Then automatically to break the junction J2 we require more voltage. So that is the reason this breakover voltage is more when comparatively VBR. So that's why we require to apply more voltage to trigger this. So this is the three modes of operation characteristics. Now other way is there, and here you can see two terms are need to explain. We can notice here the gap. I mentioned in the previous introduction, there is a two terms, latching current and holding current. What is the latching current and holding current? You can notice here, once the device is on, let it be applying voltage across that, consider that, and once the device is on, what will happen? The current will be sharply rises, no? So in this point, these two terms will the important term. If this current is minimum current is required to continue to on. Otherwise, if this current is less than the latching current, again it is going to be off state. So that's why here one term is a latching current. It is a minimum anode current is required to maintain in the on state. From this point onwards it is increasing. Otherwise, if the anode current is below this current, automatically device is come back to original state or a off state. That means it is a minimum anode current is required to maintain in the on state. So this much is a border. So if it goes below, automatically it will off. So that's why we required minimum current, this much current to maintain in the on state. That is one statement at moment. And anyhow gate case also I will explain. And other one is a holding current. So it is a minimum anode current below which device will be turn off. So that means this is the border for off, this one will be on. So that means, so if below this IH it will be off, and to maintain this much is required. Above this it will be on. So this gap, you can see this between these two latching and holding current, the gap is very minute. But if there somebody is asked in exam which current is high, 100% latching current is more than the holding current, but it is very near. Next one you can see that static characteristics only. Other one, that is what we observed in the previous one, by applying anode to cathode voltage, but not the gate. Then what is the use of gate? So if I do this way, if I open the gate, previous circuits and all you can see, I open the gate. I am applying only anode to cathode voltage, whether it is in the forward condition or in the reverse condition, whatever, I will do anode to cathode voltage. Suddenly junction J2 is breaks down, very transients will take place because it is off state to on state. No, there is a chance of getting anode voltage beyond the breakover voltage also. VBO, if the voltage reaches to VBO, then only device is going to trigger. The moment not continuously. The moment device is triggered, there is a chance of getting this voltage may beyond the breakover voltage. That's why the thyristor may damage if you do this operation to turn on the SCR. This method I call it as a forward voltage triggering. Forward voltage triggering means you are applying the forward voltage applied anode and cathode to turn on the or to trigger the SCR. That's why we call it as a forward voltage triggering method. This method is a very drawback. Chance of getting the voltage across anode and cathode beyond the breakover voltage. So that is undesirable one. That's why generally we don't prefer that. And to overcome this drawback, we make use of a gate terminal. What is the gate terminal? You can see that there is a, I am applying the voltage across gate and cathode. So here I am applying the voltage across gate and cathode, and then you can give some minimum voltage across, not required VBO now. You can give the minimum voltage here, some voltage you can give here, and now you can give some voltage gate and cathode. Then what will happen? There is a current will pass through this. By varying this voltage, you can able to increase the current, IG current. Initially IG is 0. Now you keep 1 milliampere, then you can keep 2 milliampere and so on. If gate current increases gradually, breakover voltage is going to be decreases. To maintain breakover voltage is a lower level, you can increase the gate currents. So that is the characteristic. You can see same one, previous one only, this dotted line. What is the breakover voltage relation with this? You can notice earlier, if I keep gate current is 0, then your characteristics will be like this. It goes and it goes like this. That means what? I need voltage will be VBO. Now later what I want to do is to reduce the breakover voltage, instead of VBO this much, I want somewhere here it has to trigger. This voltage is what? Lesser than this now. How it will get? I am increasing the gate current. Initially IG is 0. IG is 0, and now you keep IG1 is equal to some 1 milliampere of current. Then your breakover voltage is less than the VBO. Then IG2 you can increase, suppose, or reverse, whatever name, because this is a IG03, IG2, IG1, IG0. So that means 0, then you are increasing this, then increasing like this. So now 1 milliampere I made it. So more electrons flooded in this, it is trying to break the junction J2. So because of this gate current, the junction J2 is going to be breaks down with the lesser anode to cathode voltage. Now you can see the dotted lines in the gate current. This one is a dotted line, means gate current will be lesser. Gate current, breakover voltage will be less than the VBO, and if further increases the gate current, breakover voltage will be further decreases, and further increase the gate current, and breakover means here itself thyristor is going to be trigger if you apply more and more gate current. But how long I have to apply that way? There is a limitation of a gate terminal. Gate terminal minimum gate current as well as the maximum gate current is specified. So you have to apply only the gate current up to the maximum level. So you cannot increase further and further, only maximum gate current, IC maximum. There is specifications will give, based on that you can able to do that. So that is why you can see the characteristics now. Your characteristics, if I increase this way it will trigger, and then this way it will trigger, like this, based on your triggering voltage. So this is the one of the way you can able to trigger the SCR by using as a gate. So that's why preferably we'll use this type of triggering instead of breakover voltage. Breakover voltage, there is a chance of getting higher voltages than VBO. That's why we don't prefer that method. We will prefer only the gate triggering. By passing the gate current, the breakover voltages are lesser and lesser, so that it is simple way. It will not go beyond the VBO. So this is the general approach we can able to. Then output voltage variation through firing angle control. You can see that yesterday I told no one thing. If alpha increases, you can able to decrease your. Suppose if I delay angle, alpha is the delay angle. If you are increasing the alpha, your output voltage is going to be decreases. So because delay angle is more means output will be. This is the thing you can see now. Start with the full cycle. Now this is the full. Now your downside is what? This one is alpha. You are increasing the alpha, your output voltage is going to be decreases. You are keeping alpha is 90, half will get, or 0 full will get, and 180 0 output. So like that you can see the variation from 0 to 180 degrees of alpha, your output voltage gradually decreases. So this is just for understanding alpha versus output. Alpha increases, output will be decreases. So this is about today's class, and next class we will see other topics, turn on methods and all. So at moment we will stop this point. If you have any doubt, you ask me. Then you can give your attendance. I will download directly. If you have any doubt, you ask me, otherwise you can leave.
Sir,
Tell me, Babu.
sir, like forward conduction mode, we have also reverse conduction mode also.
Yeah, but reverse conduction mode is you are forcibly applying the reverse voltage to break that junction. There is a lot of dissipation is going to be takes place. That's why you can see that current is very sharply, but you are not able to control that current. So that is the reason that third quadrant mode of operation we don't prefer. Only
Okay.
anode to cathode. That
Okay.
is undesirable thing, but we can able to do that. If you do, the consequences are like that.
Okay.